As part of the patterns of variation, we're going to discuss about the different types of probability distribution classes. Probability distributions are a very, very major topic in statistics, as well as a big part of Lean Six Sigma projects, especially in the Analyse phase of DMAIC. Let's start by having an overview over probability distributions and the associated distribution curves. So what is a distribution? A distribution is all possible values that a variable can take. In other words, a distribution is associated with the population of interest, the population that we're investigating. What is the distribution curve? It is the boundary below which we have all possible values that a variable can take. So it is a boundary. It can be shown as a graph, or it can be expressed as a mathematical function. And the area under the curve represents 100% of the population of interest. These are some key points that we have to keep in mind. There are many different types of distribution curves in statistics. Out of memory, there are more than 300 different types of distributions, and some of them, they have names resembling medieval creatures like Loth or Lomax, but we're not going to talk about them. Now, out of these hundreds of distribution curves, there's about a dozen that are typically coming repeatedly in statistics because of their usability. And of course, out of all of them, it is the normal distribution which is the most useful and the most frequently used distribution curve in statistics and in Lean Six Sigma projects. So, if we take a look at the figures to the right, we can see that we can describe a distribution curve by using two characteristics, two parameters. One is known as skew, and the other is known as kurtosis. So if we know the skew and the kurtosis, we can determine the shape of the distribution curve. Looking at the distribution skew, if the data is normally distributed, like in the case of the bell-shaped curve, then technically we have zero skew, zero kurtosis. If the long tail is towards the right-hand side, then we're talking about a positively skewed distribution or right-skewed distribution. If the long tail is on the left-hand side, then we're referring to a negatively skewed or left-skewed distribution. Regarding kurtosis, again, normal distribution has zero kurtosis, and we have three different types of kurtosis. Platy-kurtic distribution curves. Platy is a Greek word for wide. So typically these type of distribution curves are flat and wide. We have the mesokurtic. Meso in Greek means middle of the road, etc. So these are relatively balanced in terms of flatness and width. And then we have the leptokurtic, and lepto in Greek means narrow. So these distribution curves are narrow and tall. Platykurtic, mesokurtic, and leptokurtic. Another very interesting thing is when our data is normally distributed, the three key averages in statistics, the mean, the median, and the mode, they coincide. They have the exact same value. However, when our data is not normally distributed, for example, in the case of a positively skewed or negatively skewed distribution, the location of these three statistical averages is different for the mean, the median, and the mode. And just to remind you, when we refer to mean, this is the mathematical mean, which means if we have a set of values, we add the values and we divide by the number of values. We use the mean when our data is normally distributed. When our data is not normally distributed, we use the median instead of the mean. And the median is the value that is precisely in the middle between the minimum value and the maximum value in a data set. And finally, in some cases, when we're talking about data that are not numerical, we may be using the mode or modal. And this is the most frequently appearing value. For example, if you have 5 numbers, 1, 3, 3, 2, and 5, well, number 3 is the mode because it appears 2 times. Regarding how to evaluate a data distribution, the shape of the distribution is depicted by the number of peaks and the symmetry or lack of symmetry. So skewness is a measure of the lack of symmetry or a measure of by how much the probability distribution of a random variable deviates from the normal distribution. The skewed distribution is typically either left-sided, also known as negatively skewed, or right-sided, also known as positively skewed. There are 2 types of distributions depending on the type of data that we're using. So if we're using discrete data, then we have discrete probability distributions. And in statistics, this is a type of distribution that calculates the likelihood of a particular discrete finite outcome. The distribution helps find the chances of the occurrence of a certain event. For example, how many buses are going to arrive at a bus stop within the next 60 minutes. The event is typically expressed in terms of positive, non-decimal, or whole numbers. This is a key point to remember. So, as you can see in the figure, we have an event, and we may have more than one outcome. In this case, we have outcome 1 and outcome 2. And, of course, because we're referring to a probability distribution curve, there is the probability that is typically expressed in percentages. For example, there is a 50% chance that 2 buses will arrive at this bus stop within the next 60 minutes. A discrete probability distribution counts occurrences that have countable or finite outcomes. And a classic example is the so-called binomial distribution, in which case there are 2 possible outcomes for an event. For example, if we flip a coin, either we get heads or we get tails. If we throw a fair dice. We're going to get a value that is between 1 and 6. So common examples of discrete probability distributions are the binomial, the so-called Poisson distribution, and the Bernoulli distribution. These distributions often involve statistical analysis of counts or how many times an event occurs. Continuous distributions. These are used to represent a variable that can take any value within a defined range. And again, if we go back to our training in yellow belts, when we were discussing about the different types of data, we have two main data classifications that we use in our course. We have numerical data, also known as quantitative data, and these are discrete, and the key word for discrete data is count. We can count how many bottles of milk are contained in the refrigerator. 1, 2, 3, 4. Or we have continuous numeric data, which is data measured over time, in which case the key word is measure. For example, we measure volume, we measure pH, we measure voltage, etc. So the range may be infinite or it may be finite. In the image, we can see that we have the normal distribution families. And it is very important to remember that when we talk about the normal distribution, we're not referring to one specific distribution. We're referring to a family of distributions, and each member of the family has its own mean and its own standard deviation. So in the figure, we can see a number of distribution curves that they have the same mean, but they have different standard deviation, different variance. And also, we have some other examples where you may have the same variance, but you may have different means. Speaking about the types of distributions, let's get an example. The height of an adult English male, picked at random, will follow the normal distribution, as we can see in the figure. The height of a person is essentially infinitely divisible. We could measure his height to the nearest centimeter, millimeter, tenth of a millimeter, etc. And the scale can be repeatedly divided up, generating more and more possible values. So when we refer to properties like time, mass, and distance that are infinitely divisible, these are modified using continuous distributions. And again, we have several examples of a family of normal distributions that they have the same mean but different standard deviations. I have put here a list of some of the common continuous probability distributions that we're using in statistics and in our Lean Six Sigma projects. Normal distribution, most frequently and most usable of all due to its symmetry. Log normal, F distribution, chi-square distribution, t-student distribution, etc. And remember this type of distributions when we will start talking about hypothesis testing a little bit later in our course. What is a symmetrical distribution? Symmetrical means that there is a line and the line divides the distribution in two parts, and each part mirrors the other part. So the classic and the ideal case of a symmetrical distribution is the normal distribution that has zero skew and zero kurtosis. Also, statisticians are using a particular model of the normal distribution. It is known as the standard normal distribution, and it is used as a basis for a number of statistical models, creation of statistical tables, etc. So the standard normal distribution has a mean of 0 and a standard deviation of 1. Remember, normal distribution is symmetrical. However, not all symmetrical distributions in statistics are normal distributions. There is this fine distinction. Asymmetrical, positively skewed distributions. In this case, we see that the long tail goes towards the right-hand side. And again, we see that the location of the mean and the median is not coinciding. So mean and median have different values and different locations under the distribution curve. And in the right skew distribution, we will have the mean to the right of the median. In the case of an asymmetrical negatively skewed distribution, we have the mirror opposite of what I just described. So the long tail goes towards the left-hand side. The skewness value is a negative number, it's less than 0. And the mean is less than the median, is less than the mode. Finally, we have what we call cumulative versus non-cumulative distribution. There are several ways to apply the binomial distribution to help resolve business problems associated with Six Sigma projects. One can use the relevant equations in order to help translate real-world business problems into statistical solutions, or the binomial distribution can be related to various scenarios where you could apply the binomial probability. In other words, what must be true in order to use it, or if an event is binomial, what can we infer about? Non-cumulative probability distribution function, it is about single events taken on their own. For example, a single flip of a coin that may land as either heads or tails. Referring to cumulative probability distribution function, this is about multiple events. For example, you should remember that cumulative events literally accumulate multiple probabilities for these events in order to occur. Next, we're going to explore some of the most commonly used types of probability distributions in statistics and in Lean Six Sigma. For example, we're going to cover the normal distribution, the Poisson distribution, the exponential distribution, etc. Also included in the FYI or more detailed slides are other less frequently used probability distributions, and you can use your own study time, if you wish, in order to explore further. So let's start with the normal distribution. It is also known as Gaussian distribution or bell-shaped distribution in statistics. It is symmetric about the mean, which means that each half mirrors the other half, which means that 50% of all possible values are on either side of the mean. It is the most widely used and most useful distribution in statistics and Lean Six Sigma projects. And in general, when we talk about symmetrical distributions, these occur when there is a dividing line that produces two mirror images, one on the left, one on the right. Many natural occurring phenomena tend to follow the normal distribution. So the symmetry around the mean shows that the data near the mean are more frequent in terms of occurrence than data that are far from it. And we're going to shortly come across again the empirical rule of statistics, or the 68, 95, and 99.7 rule, which states that within plus minus 1 standard deviation from the mean, if the data is normally distributed, we typically capture about 68% of all the possible values of a variable associated with common cause variation. In graphical form, normal distribution appears as bell-shaped curve. Again, in the figure, we can see what I mentioned earlier as the standard normal distribution that has zero mean and a standard deviation of 1. And all normal distributions are symmetrical, but not all symmetrical distributions are normal. This is the second time I repeat this, and it is obviously for a very good reason. You should remember that. Some data could appear as two humps or a series of hills in addition to the bell curve that indicates the normal distribution. So this differentiates the normal distribution from other symmetrical distributions. And speaking about the empirical rule, the rule states that if our data is normally distributed, about 68% of all possible values are contained between plus minus 1 standard deviation from the mean, 95% between plus minus 2 standard deviations from the mean, and 99.73% of all possible values are within plus minus 3 standard deviations from the mean. So based on the empirical rule, anything that is beyond 3 standard deviations becomes more and more rare. And this has to do with the anatomy of the normal distribution, because the two long tails, they go to infinity, to the right and to the left, without ever crossing zero. So you have to consider the plus minus 3 standard deviations as the two stoppers that capture the majority of almost all common cause variation in a process. Another very common type of probability distribution is the binomial distribution. So it is a discrete probability distribution that summarizes the likelihood that a value will take one of two independent values under a given set of parameters, or what is known as assumptions. So the distribution measures the probability of a number of successes or failures outcome in an experiment in each try. So the binomial distribution means that we have two terms. We're interested both in the number of successes as well as the number of attempts. For example, if we flip a coin 10 times, what is the probability that we're going to get two twos? Two heads. Each is useless to us without the other. The distribution only counts two possible states, typically represented as 1 for a success or 0 for a failure, given several trials in the data. We can see in the figure the shape of the binomial distribution, and one thing that you will notice is if we compare it to the normal distribution, it has one peak. But if you look at the binomial distribution, because of its nature, it has two peaks. That's a very easy way to distinguish visually between normal and binomial. So what are the requirements and conditions associated with this type of probability distribution? The first one is the number of trials is fixed in advance. For example, the number of times that we're going to flip a coin must be determined before we start the experiment. Probability of success should be the same on every trial. Only two possible states or possible outcomes, true or false, hot or cold, success or failure, etc. So we have two possible outcomes. Independent trials, which means that trials are statistically independent from each other, and the probability of success is constant. So we use this type of distribution when you're sampling with replacement, and remember that continuous data is not binomial data. So it is often used in social sciences, statistics as building block for modeling the dichotomous outcome variables. For example, whether a Republican or a Democrat will win an upcoming election in the United States of America, whether an individual will die within a specified period of time from a particular illness. Poisson distribution. It's not Poisson, it's Poisson. That's in French. So this probability distribution is used in order to determine how many times an event is likely to occur over a specified period. For example, how many people are likely to come into my office within the next 30 minutes or within the next 60 minutes? What is the probability of one person, two persons, or 0 persons walking into my office? It is count distribution. In other words, we use discrete data, and it's also used to understand independent events that occur at a constant rate within a given interval of time. The Poisson distribution has been named after a French mathematician, Denis Poisson. This type of distribution is a discrete function, meaning that the variable can only take specific values in a potentially infinite list of values. One of the key parameters of the Poisson distribution is the so-called lambda. And as you can see in the figure, for different values of lambda, the Poisson distribution assumes different shapes. For example, if we use the lambda value of 1, the Poisson distribution looks like an exponential distribution. If we use an average value of lambda equal to 4, this looks more likely like the actual Poisson distribution. But if we increase the lambda to 10, the shape of the Poisson distribution is very, very close to the shape of a normal distribution. So many economic and financial data appear as count variables, and they're lending themselves to analysis by using this type of probability distribution. So here we're referring with characteristics that can, at least theoretically, take large values, but instead they may take small values, and these are associated with this particular probability distribution curve. Here we have a couple of examples. If the average number of people who buy cheeseburgers from a fast food chain on a Friday night at a single restaurant is 200, a Poisson distribution can answer questions like, what is the probability that more than 300 people are going to purchase cheeseburgers from the same restaurant, from the same fast food outlet? Another example, if you go to a video store, it averaged 400 customers every Friday night. So in a case like this, the Poisson distribution can answer a research question like, what is the probability that 600 customers would come in at any given Friday night? So these are examples, and these are the types of research questions that you can answer by using this probability distribution. It is a very classic example of using the Poisson distribution, and this is historic. They used it in order to estimate the annual number of Prussian cavalry soldiers that were killed due to horse kicks. Some modern examples may include estimating the number of car accidents or car crashes in a city of a certain size, population size, for example, 500,000 people, or calculating the probabilistic frequencies of different types of neurotransmitter secretions, if we refer to the field of physiology. So we use this distribution when you want to estimate the likelihood of a number of events occurring within a given time interval. The basic assumptions, we use discrete data, so we refer to a discrete probability distribution. Events are classified either as success or failure, and the length of the observation periods is fixed in advance. Occurrences are independent from each other. Events occur at a known average rate, which is known as lambda, and this is often referred to as the average arrival rate, abbreviated AAR. By the way, the Poisson distribution and the exponential distribution are extensively used in queuing statistics or in the queuing theory, where queues can be formed either by people or by things like packages or emails. The exponential distribution. On the figure, we can see how the exponential distribution looks like. So in probability theory and statistics, this type of distribution is defined as the probability of time between events in the Poisson point process. So this distribution is a process in which events happen continuously and independently at a constant average rate. It is widely used in statistics as well as in Lean Six Sigma projects and other fields of science. It is considered as a special case of the gamma distribution and the continuous analog of the geometric distribution. So exponential distribution helps us determine the time elapsed between the events. In other words, if we're waiting in a bus stop, how long will it take before the bus arrives at the bus stop? Example, the amount of money spent by a customer on one trip to the supermarket, it follows the exponential distribution. And again, we see that based on the key parameter value, the exponential distribution assumes different shapes. When we refer to the graph associated with this probability distribution, the probability density function shows the distribution of distance of time taken between consecutive events. So these two terms are used in the exponential distribution graph as the lambda and the x. So in the example that we have in the figure, the lambda represents the events per unit of time and x represents the time. So the graph shows the values for lambda equals 1 and lambda equals 2. So where do we use this? It is used in a fairly broad range of applications, such as reliability theory, queuing theory, physics, etc. Calculating the mean time between failures. It follows the exponential distribution. Bus arrival times. they follow the exponential distributions, etc. So what is the difference between the Poisson distribution and the exponential distribution? Because although they have some similarities, they are different. The Poisson distribution deals with the number of occurrences of events in a fixed period of time. On the other hand, the exponential distribution concerns the amount of time until some specific event happens. So this is the distinction and the main difference between the two.